This is a screen we developed for a prime power site. It includes dual generators, functioning as dual mutual standby. There is no utility power at this site, so when one generator is running, the other is on hot standby, ready to take the load, in the event of a failure. These type of sites present some challenges in terms of control logic, and in terms of scheduling maintenance, as one engine is always running. At the bottom of the screen, we have our typical alarm log, and navigation buttons. Across the top, we can see that we have the last pole for each generator, A, and generator B. Next top center we have our site ID and site name, followed by twin interleave buttons and twin pole indicators, one for each generator, and finally the host current time. The indicator for generator, B, running is yellow, while red is reserved for warnings and shutdowns, and the indicator for generator, A, is gray to indicate it is in a standby state. We have statistics on each generator for run hours, starts, and total kilowatt hours produced for overall totals, today and yesterday. The same is reciprocated on generator B on the other side of the page.
The transfer switch senses the instant power in kilowatts, current in amperes, voltages in volts AC, as well as frequency in hertz. If any of these analog meter devices falls outside of the normal operating range, this indicator will go dark, and the load will be released. The other generator will start and warm up, this indicator will illuminate, and after the warm-up cycle, the load will be transferred, and this indicator will illuminate. The load at this site is similar to other sites, where the rectifier charges a battery bank that is always online. This will ensure a smooth transition, in the event of generators needing to stop, or start, providing 100% uptime. The starting battery voltage, oil pressure, cylinder temperature, and generator room temperature are also included, to assist in detecting any issues. This metering is completed for both generators, and semi-annually the generators are switched so that generator A would run prime, and generator B would function in a standby capacity. We also have for each generator indicators for alarms, warnings, shutdowns, and emergency conditions that will turn red in the event they are tripped.
In telecommunications sites, environmental controls represent nearly 50% of total power consumption. Free air cooling HVAC units are being implemented that can demonstrate a substantial reduction in power costs and increases in efficiency. When deploying new technology, it is recommended to carefully analyze the first installations until the technology is satisfactorily proven. In some cases, we have been deployed to monitor DAC's free air cooling HVAC units and to complete a cost-benefit analysis. We will look at one such screen. Top left, last pole indicator and initials to indicate this is a DAC's HVAC unit, followed by the site ID and name in the top center position. Next the interleave button and indicator, and then by the host date and time.
For those who are unfamiliar, I will cover the basic function of this unit. On normal operation, the supply fan is on 24 hours a day to keep air circulating. When the temperature rises above the target temperature, the unit will free air cool, which means push hot air from in the building to the outside, and bring cooler air from outside into the building. This eliminates the compressor used during DX cooling in normal air conditioners, which offers a substantial reduction in power consumption. If the free air cooling capacity cannot keep up with the load, then it reverts to DX cooling to attain the target temperature. In DX cooling, refrigerant is compressed in a power-hungry compressor, where it picks up heat. The hot refrigerant crosses an outdoor condenser coil, where a fan pushes outdoor air across it to cool it down. The refrigerant then crosses a thermal expansion valve, or orifice, to drop the temperature drastically through the pressure change. Then it enters the evaporator coil. Warm air in the building is ducted across the cool evaporator coil, which cools the air, and at the same time warming the refrigerant, and the cycle repeats endlessly. Also, if the temperature drops below the target, A heating element is energized to make up the difference.
On the left, we have our active set points, which start with a target temperature and have a differential setup for controlling heating and cooling cycles. In this case, 1 degree above target, cooling starts and scales to its maximum cooling capacity 3 degrees above target, followed by a high alarm 6 degrees above target. Retroactively, the heating set points are set up in a similar fashion. There is an indicator for the supply fan, which includes its percentage of full operation. The condenser fan indicator also correlates to percentage of full operation. The compressor animation is digital, on or off. The primary animation is a moving graphic that indicates the current state of the ducts. We are measuring our return temperature and displaying min and max for today and for yesterday. Outdoor ambient temperature is also metered, and the min and max for today and yesterday's min and max are displayed as well. Next is the high pressure side of our refrigerant, and displaying our min and max values for today and yesterday. We are also recording our compressor run hours, free cooling hours, heating hours, supply fan and condenser fan run hours for today, yesterday, and overall total. This allows us to compare min and max values and to plan service intervals based on actual run times. This graphic is exceptional at providing a reduction in maintenance costs by allowing our HVAC technicians to monitor site efficiency and deploy service personnel accordingly.
The power and value of our system is illustrated further with the use of our trending engine to review datasets to identify specific patterns. This can be illustrated here. We can quickly identify the correlation between outside ambient temperature and return temperature as it impacts the duty cycle of free air cooling. Particular types of problems such as a reduction in compressor or fan efficiency over time can be identified by certain qualifiers in the data. We can automate the process of finding these qualifiers or comparisons over time and flagging them for further review. This has proven quite successful in providing value for a targeted maintenance program, rather than the typical, random, or shotgun approach.
Battery uninterruptible power supplies is a substantial consideration for telecom sites, particularly on sites housing critical infrastructure. These batteries typically offer upwards of 48 hours of runtime during emergency service to allow a reasonable amount of time for a contractor to get to site and take corrective action in the event of a failure. We have developed our own battery bank in the 50 kilowatt range that includes a full SCADA system to allow remote assessment and control. We have deployed a balancing system that leverages our capabilities against industry challenges to ensure uniform battery charging and discharge. We will look at a screen that we developed for this technology here. As usual, we have the last communication with the site in the top left corner, followed by the site ID and name in the top center position, and the interleave button and indicator, and finally by the current host time. Across the bottom, the alarm log and standard navigation buttons are present. Our real-time values here are mirrored on our site overview screen, which include real-time values for total bank voltage, average cell voltage, and estimated state of charge. In real time, we have our max, min, and mean values on a cell-by-cell basis for DC voltage, temperature, internal impedance, as well as balance, as a percentage of current bypassing capacity. In the lower portion of the page, we have access to real-time data on each individual cell in the bank. These are 12-volt cells tied together in series to make 9 independent 48-volt strings. Without our unique balancing technology, this would cause cells to charge and discharge at uneven rates, which would promote premature failure of some cells, resulting in an untimely reduction in capacity or potentially a catastrophic failure. At a glance, we can compare extreme values for today versus yesterday, We also have access to trending to view historical data to identify points in time where changes may have occurred. This trending is especially useful for identifying long-term changes in capacity and internal impedance, changes that may trigger advanced maintenance or warranty work. Simply to avert an outage at all costs is definitely a fundamental component of operating a UPS system on critical infrastructure.